Okay, so here we go today. So what we have been seeing is we have been having we have been you know I mean not really working things out, but giving you glimpses of what the ADS CFT correspondence, or I mean in more general the holographic principle is, gave you a little bit of an idea of what ADS CFT is. Just to remind you, and last time we looked at the geometry of ADS, and there I told you that what is happening is, if you look at this very sort of the first image on Google that springs up when you're looking at ADS CFT, this is the thing that you get. And here what is saying is that inside of the bowl there is a theory with uh, gravity, in this case string theory, and on the surface of the bowl there is the theory without gravity. I wouldn't call it particle theory, I would call it conformal field theory. So that is what it is. And the major lesson, the first sort of building block of things where things actually match up, is when you say that, let me just, so ADS, let's say gauge gravity duality. So here, the first thing that is, so first, number one, is matching of symmetries. Okay. And by this, I mean the isometries of the bulk space-time will be equal to the global symmetries of the boundary. Okay, we saw this in the case of ADS, where isometries of ADS where if this is d plus 1, then this is SO d2, and the global symmetries of the boundary, symmetries of CFT in d dimensions is also equal to SO d2. So you see, so from here, we can have an idea that ADS d plus 1 is sort of equal to CFT d. We lose way of trying to write it. And we also saw last time around that going beyond this, you can actually, what you can do is matching of partition functions. And what we wrote down schematically was Z gravity was equal to Z CFT, or Z field theory, if you wish. And I showed you an example where you look at the bulk, and you have some scalar which is in the bulk. So you might not really understand why I'm drawing cylinders out here, but I urge you to try and look at this a little more carefully. ADS spacetimes can actually be represented on something which is called the Einstein static universe, and I'll try and give you guys some references for this. But the point is that you could have, field, for example, a scalar field in the bulk, and you can evolve it. And once you solve the Klein-Gordon equation, then you'll see that there are these two modes, and one of them is a normalizable mode, that is, it dies off at infinity. One is a non-normalizable mode, and that becomes constant on the boundary. We will call that phi naught. And this particular phi naught acts as a source of some other operator O in the field theory. So what is going to happen is, with your action S, field theory, if you wish, you need to add your S, so let's say S total. Okay, let's keep it at that. So let's say this is S CFT plus this phi naught O. I mean, you need to obviously integrate it. So this is a source for this particular operator, and this is sorry, and O is this field that is the one which actually is dual to this field, this thing which is the field in the bulk. Okay, so there is an operator dual to this field in the bulk, and you can, for example, figure out what the endpoint functions in your field theory is by doing an analysis on the bulk side. I didn't go into the details of it, but I gave you a very brief sort of idea of what to do. All right, so that was that for yesterday. I mean, the last day. So, and I showed you a few metrics and so on and so forth. But the thing that I wanted to do on the last day is link up things a little bit more. Okay. So the emphasis of the principal part of our course has been two-dimensional CFTs. Okay, what do I write here? As we have seen so we want to figure out what is going to happen when we look at three-dimensional ADS, which by the holographic principle is supposed to be dual to the two-dimensional CFTs. Okay. So that's what our focus is going to be on this in this last lecture. So let me try and just read out what I've written here. So as we've seen, the initial building blocks of the gauge gravity duality was this matching of bulk isometries with the global isometries of the lower dimensional field theory. Okay. And as I stressed, for ADS D plus 1, the isometric group is SOD, which is also the group of global isometries of D-dimensional CFTs. Now remember, when we're looking at two-dimensional CFTs, we have this emergence of infinite dimensional symmetry. So you have two copies of your WIAT algebra that emerges, and this has been sort of the principal reason why there was so much of a simplification or so much of an analytic handle that we could have in this case. Okay, so the natural question is there a similar infinite dimensional enhancement for symmetries in ADS? Okay, I think I have missed symmetries. Okay, let me just write off. A priori, it's sort of unclear how this actually happens, because the isometries of ADS3, if you just look at the metric of ADS3 and figure out what the isometries are, you'll see that this is SO22. This is not infinite dimension. Okay. So we have to work a little bit more to try and understand what is going on. Okay, so again, this is going to be a little hand wavy, and I'll indicate a few of the steps, but let's go ahead with this. Okay. So the isometries that we spoke about of ADS3 actually map to the global subgroup of, this two copies of the Virasoro algebra. So this actually amounts to L0, L plus minus 1, L0 bar, L plus minus 1 bar. Okay. So these are the ones that give you the 6 isometries of, ADS3. If you want to get the infinite dimensional algebra, one needs to look at symmetries that emerge near the boundary of ADS. Okay, so this is what is called these symmetries are what are called asymptotic symmetries, and as I said, symmetries at the boundary of the space-time. So what is it that we do? So remember that any sort of symmetry transformation is by and Noether's theorem is related to a charge. Okay. Now what we want to do is we want to so now if you are given a set of boundary conditions, you will have so what you'll have is there are particular diffeomorphisms which are going to respect these respect these boundary conditions, and you can associate a charge for each of them. So now what you have is the asymptotic symmetry group is the set of allowed diffeomorphisms by the set of trivial diffeomorphisms. Now, what do I mean by this? As I can say, any diffeomorphism is associated with a conserved charge. Now, when this particular charge is 0, these diffeomorphisms will be called trivial diffeomorphisms. So in a sense, the asymptotic symmetry group is going to capture only those diffeomorphisms which are going to have non-trivial charges. Okay, so that's what this is. And so this is the important thing. Okay, so this is what is called the asymptotic symmetry group. Now what is important is that the states of the quantum theory that we are going to define of gravity will fall under representations of this ASG. Okay, that's what happens. Now what we will very quickly do is look at what the asymptotic symmetry group of ADS3 is. Okay, so for this we first again need to figure out what are the boundary conditions we need to impose. Again, there will be some words I will not be I will not be in a position to explain all of these things, but I will try and send you some more references for you guys, for those of you who are interested to read on more. All right. Okay, so three-dimensional gravity, and in general, gravity in lower dimensions has many peculiarities. You may have seen this when you were trying to look at the degrees of freedom of the graviton in d equal to 4. Maybe I don't remember if I actually showed this in my lectures. Probably not. But you can do a reasonable straightforward counting, and you can figure out what the degrees of freedom of Einstein gravity is for any dimension. And the weird thing is, if you look at d equal to 3, those number of degrees of freedom become equal to 0. Okay. So what does this mean? This means that three-dimensional Einstein gravity has no propagating degrees of freedom. There are no local degrees of freedom, so there are no propagating waves. So in 3 dimensions, 3 as in 2 spatial and 1 time direction, there are no waves. Okay, there's something even more interesting and sort of astounding is if you try to take the Newtonian limit in d equal to 3, things don't work out, and there is no Newtonian potential, and weirdly enough, the masses will not attract. This is in a sense linked up with the fact that gravity becomes attractive because of this propagating spin to field, basically. So that's another thing that I have in mind for you guys to actually read. I'll send you some particular material. So you would think that if there are no propagating degrees of freedom, it's a very trivial sort of a theory at the end of the day, right? But it turns out that gravity in 3 dimensions is very far from being trivial, and we will see this, that we'll not see the fact that that's due to the topological properties, but gravity in ADS actually will contain black holes, and these black holes are called Banyados, Teitelbaum, and Zanelli black holes, or BDZ black holes. So if you were to think of some boundary condition, it better be that these particular boundary conditions are such that we do not exclude these guys. Okay, so the interesting solutions in phase space should not be excluded by our boundary conditions. So that's something that we need to keep in mind. Okay, so what do we do? So we want a set of boundary conditions, for example, that includes these BTZ black holes, and of course also includes also includes the global ADS3. And the asymptotic symmetry group that I'll get out of this should at least have the isometries, right? It should at least have the SO22. So a set of boundary conditions that has proved to be extremely useful is the one that was proposed by Brown and Helon in the 80s. And let's see a little bit more about this. I will try and indicate what the steps are, and I will actually leave it to you guys as an exercise to fill this up in. Okay. Now, this is a theorem that any asymptotically ADS3 spacetime can be written in the neighborhood of the of the boundary as the following. Okay, here L is the radius of ADS, and so this can be written as L squared rho squared e to the 2 rho into G naught AB dxa dxb. G naught AB is going to be what the metric on on the boundary, and then since this is multiplied by e to the 2 rho, there are some subleading terms which go as e to the rho. Okay, you can also write it in terms of more familiar radial like coordinates, and there you can just write this like you can rewrite r as L into e to the rho, and then it becomes L squared dr squared by r squared into r squared by L squared into this guy. So this is more familiar with from what things we had done earlier. But this is what an asymptotically ADS in space-time is going to be. And here rho is a space-like coordinate such that rho goes to infinity actually represents what the boundary is. And these x's, as I said, are the coordinates of the boundary. And the what is happening at the boundary is dictated by this two-dimensional metric G0AB. Okay. Now what do we have to do? So now in this particular framework, this Brown-Hano boundary conditions simply boil down to saying that this particular metric at the at the boundary is fixed to be a flat metric. Okay, this is sort of like a Dirichlet condition on the metric, and it's fixed to be flat. Now remember that our set, so if we are to find the asymptotic symmetries, what we have to do is that we have to preserve this form of the boundary metric. Okay, so any particular diffeomorphism that you have will have to preserve this form of the metric. So let's try and see how we can do that. Okay, so now we can look at an arbitrary diffeomorphism, and that xi is going to depend on rho, and it's also going to depend on these x's. X's are your x's are your boundary metric. So now what is so the things that you're going to keep in mind is, so this is the part that you have to actually work out for yourselves, and you will see that this essentially means, so the Lie derivative on the different parts of the metric will have to preserve the structure which you have have fixed. Okay, so that would mean something like 7.22, and this is going to be a part that you, so these are going to give you some equations which you need to solve to then find out what L of xi is. For example, it's straightforward to see that for let me just explain one thing. So if you're looking at GAB, for example, so the GAB has been fixed, and so you should, so this has been fixed as being flat, but you could have some small fluctuations here which go as exponential of rho. So this L xi of G naught AB has to be fixed up to something which is order of exponential of rho. Okay, so this is going to be something that I will leave to you guys to try and sort out. This is going to be hopefully a fun exercise for you guys to do. So you are going to get some equations from here, and you need to solve these sets of equations to obtain a form of this arbitrary diffeomorphism. Okay. Now you can write the boundary metric in terms of light cone coordinates, where x plus minus is t plus minus phi. And you can re-express the xi which you wrote in rho and xa in terms of rho and x plus minus. Then you are going to get something like a xi plus minus here. And again, you can re-express these guys in terms of Fourier modes. So if you do all of this, which is reasonably straightforward to do, then you are going to get a form of these Fourier modes xi m. and you can figure out what the I mean what if you're given the form of xi-m, you can figure out what the brackets would be, and lo and behold, what you find is that if you solve this, what you're going to get is the WIAT algebra. Okay, so if you find out what what the brackets are between the xi's, you are going to get two copies of the WIAT algebra emerging from the asymptotic analysis of ADS3. So let me just pause once and let me remind you of what exactly I did. So I said that asymptotically ADS spacetimes are given by a form of the metric like this. These are called Pfefferman-Brown coordinates, and the Brown-Hano boundary condition amounts to fixing G0 AB as being flat. So it's sort of like fixing Dirichlet boundary conditions of of the metric. You fix it, not to fluctuate at the boundary. So now what you want to do is you want to look at a set of set of diffeomorphisms of this. And once you do that, so the thing that you need to keep in mind is that the form of the metric has to stay the same. So so you are going to have restrictions on the Lie derivatives of the metrics uh, of these particular pieces of the metric. As you can see that the rho squared piece is something that has just constant which is multiplying it, so that should not change. So this is just L xi acting on G rho equal to 0. G rho A is something, so the cross term is not there. So that essentially would mean L xi acting on G rho A is equal to 0. And we have fixed the GAB, the GAB term to be flat. That would mean that this particular this has to stay put once we look at some particular diffeomorphisms trying to change the boundary metric. It can only do so up to this order exponential of rho. So the equation that you'll have to solve here is L xi acting on GAB, giving something which goes as exponential of E rho, okay, an exponential of rho. If you solve these equations, you get a form of xi. And then what I said is that you write xi in not rho and xa, but x plus minus. If you do that, you're going to get the xi and xi plus minus, and you can break this up into Fourier modes, and the algebra that you have for these modes actually follow the these give you two copies of the WIAT algebra. So you have the WIAT algebra emerging from an asymptotic analysis of ADS3. A lot of this is very new to you guys. So if there are any questions, I'm happy to try and address them.
Yeah, I have a question.
Yes.
Like where exactly have we used the conserved charge corresponding to the xi? Like that
Not
charge
yet.
algebra? Not
Not
okay.
yet. Not yet. So what is going to happen is so you see that this is the WIAT algebra, right?
Right.
So what is going to happen is that all of these things will also have a corresponding. So since all of these are sort of symmetry transformations, they're going to have corresponding, I mean, charge which is actually associated with them. Okay.
Right. Right.
And the charges will also close to form the same algebra,
Okay.
except for the crucial fact. I mean, this is what I actually write down next is yeah, the algebra of the charges, I mean, associated with the phase space will yield a representation of the same algebra. This is again a little too far for me to do in this one little class. But this algebra is now going to be augmented with central extensions. Okay. So what is going to happen if you just look at, I mean, if you just look at what the algebra of these particular diffeomorphisms is, that is the WIAT algebra. But if you're looking at the charges, you get the emergence of a central charge piece from here. This is the I mean famous Brown central term, and what you'll get is C will be equal to C bar, and you'll also get the factor that you get from here is 3L by 2G. L is the radius of ADS, which I have not written down anywhere. I think L is equal to radius of ADS 3. So now this forms our first hint that a quantum theory in ADS3 is intimately related to a two-dimensional, I mean, conformal field theory. As I've written here, it should be noted that this discovery of asymptotic symmetries of ADS3 far predates the discovery of in ADS-CFT. This predates it by more than a decade. And it can be regarded as one of the principal precursors of, I mean, of this, I mean, ADS-CFT correspondence. Okay, so this is how these infinite dimensional symmetries arise in three-dimensional ADS. It doesn't. I mean, it arises when you go near the boundary. You remember that in a CFT as well, the two in a two-dimensional CFT, the only sort of globally well defined things where this L0 and L plus minus 1, those remain the isometries of three-dimensional ADS. Once you go near the boundary of ADS, all this infinite dimensional symmetry starts to emerge. So I have not written this down anywhere, but remember that three-dimensional ADS does not have any propagating degrees of freedom, but there's stuff happening on the boundary. Okay, so these guys will give rise to what are called boundary boundary gravitons and so on and so forth. So all the fun is, I mean, in a sense, near the boundary. For those of you who are familiar with something like Hall effect, this might start to ring a few bells. Even there, I mean, the charges don't flow inside, but on the boundary. So it's similar to that. Okay. Uh, so that's something that I just wanted to say. And now that we have this sort of proposed link up between CFT and CFT in 2 dimensions and ADS in 3 dimensions, the natural question is, can we actually push this a little more? You can, and with what we have already learned in our course, we will be able to see something really fun. Okay, so let's actually pause to try to get to that. So the thing that I was saying to you guys earlier is that there are these black holes. Okay, there are these black holes in three-dimensional ADS, and I'll write down the metric for you. Okay, so the metric is going to be given by a form like this. So this is, if some of you are familiar with the I mean, ADM decomposition, this form would already be, I mean, be sort of familiar to you. But for those of you, I mean, most of you who are not, just think of this as a black hole like I mean, black hole like metric, right? So if you for the moment, I mean, disregard this, then you see that, you know, this part of it is like your usual, I mean, Schwarzschild like thing, right? So your Schwarzschild case, if you I mean, if you remember, that is ds squared is equal to some minus you know 1 over so r minus so let's r minus twice m dt squared plus dr squared. Let's call these blackening factors, if you wish. Let's call this a blackening factor, so that we don't have to get in. So this, yeah, so this is like f of r, if you wish, dt squared plus dr squared by f of r squared plus r squared d omega squared. And the signature for something happening, something weird happening, is I put some squares here. Let me get rid of the squares. So sorry. So the signature for something weird happening is the factor in front of this GTT. I mean, actually goes to zero, or yes. So that's a signature for this. I mean, so there's going to be an event horizon and so on. And if you have rotations as well, then you what you find out here is that you get some extra terms. Okay, so now, yeah, I mean, all of you know this well, so let me not just repeat usual Schwarzschild stuff. But what is happening here is that this particular metric is of a form like that. Okay, and this is sort of like the three-dimensional analog of the, I mean, Kerr metric. And if you so m and j that I write down here are the mass and angular momentum of this black hole. Good. So now, since this is very much like a Kerr black hole, what is going to happen is that this is going to have, so okay, so let's just do a few sanity checks. Number one is if you're, so if you go far away, so if you go I mean, if you take r out to infinity, then you see that you can easily drop this term, and you can of course drop this term, and this term also will just go away. So what you end up with is r squared over L squared dt squared plus L squared dr squared over r squared plus r squared d phi squared is equal to 0. I mean, so the metric r going to infinity metric goes to this. This is clearly the thing that you have seen before. So this is clearly the three-dimensional ADS thing, which is also emerging here. Okay, so these, I mean, space times are, I mean, asymptotically ADS3. And you can also see that, you know, if you put n equal to n of r is equal to 0 and n phi of r is equal to 0, then you find that you will get ADS3 as well, right? So you can put sorry, let me just have a look at this. No, n of r is not 0, n of r is 1. I'm sorry, what am I doing? N of r is equal to 1. Yeah. So if you do that, then you're going to find that you reduce to three-dimensional ADS. I think I've written something wrong out here, so let me just correct that. So this is a black hole solution in three-dimensional ADS. Okay. There are a lot of interesting things that you can actually find out from here. So n is not equal to 0. N is equal to 1 and n phi is equal to 0, which translates to j equal to 0 and m equal to minus 1 over 8. This is going to be just the global three-dimensional ADS, and in this case, r equal to 0 is just the origin of the polar coordinates, and there is no singularity. For those of you who are interested, there is a lot more to be understood, and a lot of more fun to be had with the BDZ metric, including what the causal structure of the space-time is, and so on. Those of you who are inclined can go back and have a look at this. This is extremely interesting, to say the least. Okay. Now, as I said, this is a solution which is very similar to the rotating Kerr black hole in 4 dimensions, and like the Kerr black hole, it is going to have an inner horizon and an outer horizon, and you can solve these equations to find out that the inner and the outer horizon. The expression for this is given in terms of G, L, M, and J in this by this equation. Okay. So that is what the inner horizon and outer horizon is. Now remember our very brief encounter with black hole thermodynamics, and that yields that the entropy of a black hole is its area by 4, right? Remember, this was sort of like the guiding principle behind the fact that there could at all be be some holographic theory, because the degrees of freedom of this theory are less. That's because the entropy of a black hole goes like its area. So it essentially goes like its area by 4g. So if you're looking at the BTZ, this is going to be the area of the outer horizon by 4g. And remember that we are in 3 dimensions, and 2 plus 1 dimension. So r equal to r plus is actually a circle. So that essentially means that you're going to have the area of the circle, if you wish. So it's just 2 pi r plus, right? So it's the perimeter of the circle, if you wish. Yeah. So that's what it is. So the entropy of the BTZ black hole is 2 pi r plus over 4g. Okay, that's what this is. All right, so now comes our clincher. Okay, remember what we did when we are doing this modular invariance and so on and so forth. So 2-dimensional CFTs, there is something that you have learned. It's called the Cardi formula, and that relates the entropy of a 2-dimensional CFT with the central charges and the weights. So given what your central charges are and given what your weights are, you should be able to find out what the entropy of the system is. Okay. So the black hole, if you wish, is dual to it's a state which it's a highly energetic state. It's dual to something on the field theory side, and now so again, it's a very natural thing to sort of associate the mass and angular momentum of the black hole with the uh, corresponding high energy state in the field theory. And so H plus H bar is going to be given by L times M, and H minus of h bar is going to be j. You could ask me I mean, how I got this, and for that I can sort of take you back. I mean, this is I mean, in a way, so that's something that we could go back and figure out, where was this. So remember that we had done a mapping between states and conformal dimensions, uh, and we found out a formula which remained which relates the conformal dimensions with these dimensions of I mean, space time, and the radius of ADS plus the mass. When you so now what you would have is you would have d equal to 2. So this just becomes delta plus minus is 1 minus plus minus root over 1 plus m squared over m squared r squared, or in this case m squared l squared if you wish. Let's get rid of the L squared. And you remember that we are looking at very high, I mean, high energy states. So you are going to drop the 1. So you can see that delta is going to go like m into L, right? So that is what we have, and delta is h plus h bar. So that's another way of trying to see that this actually gives you the right thing. So the mass is going to be related to h plus h bar, and the angular momentum is going to be related to h minus h bar. This is, I mean, of course, what you expect. All right, so what we have now is that we have said that the mass is going to be h plus h bar, the angular momentum is going to be h minus of h bar, and the central charge C is going to be 3L over 2G, right? So let's put all of these things in, and then what do we find? So let's do this. So this is this. So let's just take another page. So S Cardi is what is it? 2 pi square root over CH over 6 plus C bar H bar over 6. Okay. H plus H bar is equal to Lm. H minus H bar is equal to J. So H is equal to Lm plus J. H bar is Lm minus J twice. There's some factors of 2 which I've missed. And now you plug these in, and what is going to happen? Where did I mess up a factor of 2? I seem to have messed up a factor of 2 somewhere, but let's see how this goes. C is equal to 3L over 2G. C bar is equal to 3L over 2G. Plug these in. So S Cardi is 2 pi into square root of 3L over 2G. There is a factor of 2 which I'm missing. Let's put Lm plus J into, so there is a factor of 2, and there is 1 over 6 into 3L over, okay, 3L over 2G is done. Okay, maybe I've missed a factor of 2 outside somewhere. Okay, so that means that this is 2 pi into this is so Lm, so square root of L over G into there is this 2 which also goes off. So this is 6, that's 3, So there's a factor of 2 down here. Let me put the factor of 2 here. So there's a factor of 2 going out there. And when the dust settles, what you're going to get is Lm plus j. And then the other one, once you do this, is going to be plus of root over Lm minus j. And then you will find that this is nothing but just pi r plus over 2g. Okay. So once you put your factors right, I think I may have missed a factor of root 2 in my expression for r plus. But the upshot is that once you put all of these things in, BTZ, I mean, the Cardi entropy is something that reproduces your Bekenstein-Hawking entropy of the BTZ black hole. So this, if you wish, forms one of the first checks of this ADS-CFT correspondence, that you can actually get quantities in the bulk by doing some analysis in your field theory. Okay, you can push this more and more. You can find lots and lots of things that are going to match between the bulk and the boundary. A lot of the times it's very hard to find things. So some of the aspects of ADS-CFT is something that I've not said. It is, so the field theories that you find are actually dual. Are actually, so there is a link up. So why this duality? On the one hand, why is it so useful, and on the other hand, why is it so exasperating? Is that it sort of links two sides, in the sense that it links strongly coupled region of one theory with the weakly coupled region of the other theory. So if you were to have some sort of so your field theory, for example, can be very strongly coupled, and that is going to be dual to something in the bulk which is going to be extremely weakly coupled, essentially Einstein gravity, supergravity if you wish. And what you can do is, by doing very simplified analysis in the bulk, in this higher dimensional anticipated bulk, you can read, you can actually say things about strongly coupled field theories, which otherwise you would have found almost impossible to do. Why is this also exasperating? It means that you can, unlike the thing that we have done out here, which is just based on symmetries and so on, and it was, a sort of rudimentary check. Trying to prove this is extremely hard, because you cannot, always attempt things on both sides. Okay, you cannot really calculate something, except for extremely quantities which are protected by symmetry. You can't actually look at arbitrary things on the field theory side and say, look, okay, so we have been able to match them. So there's this interplay, which is on the one hand extremely useful, and on the other hand extremely exasperating. So all of these things, so form what the research on this particular field has been looking at for the last 20 years or more. So that's where we are at. So we have now come to the end of the course. I hope I was able to give you an idea of what is happening. Why CFTs are useful, and what are the basic techniques which are useful for CFTs in all dimensions, and especially in CFTs which are in lower 2 dimensions. So let me just stop with this particular thought where we had begun. So this is where we had begun our course. So let's remind ourselves of this. So we have, in a sense, seen how CFTs are linked to all quantum field theories by these renormalization group flows and so on, which we spoke about earlier. And we have also investigated this half of the, I mean, of this chart. In the sense, we have seen a little bit about string theory and how CFTs are useful for string theory. And we have also seen at the end of the day a little bit of, I mean, ADS CFT and how things are actually, how CFTs are central to that. You can obviously see my bias in this, that I did looked at this half and not, for example, at this half. If we had some more time, I would have actually loved to say a bit more about statistical mechanics, but maybe that's something that you guys can read up. And there is this interesting, I mean, window about CFTs and their relationship to, I mean, cosmology, which I also, would urge you, if those of you who are interested, you can explore that. If you're interested to speak about somebody, I mean, speak to somebody who has actually done this, I would suggest that you drop Niloy Kundu an email. He has actually worked on this. So yeah, so that's where we are at, and I hope this was useful. And I hope I have been able to, I mean, sort of justify why CFTs are amongst the most powerful tools in all of theoretical physics. And I hope this has been fun, actually. So that's that from my side. So if there are any questions, please go ahead. And if not, yeah, so if you have some things to ask, please go ahead. All right, seems that
Yeah,
everybody
so like
connected. Yeah, please, yes.
I have this question, but I don't think like this is related to our discussion. But
Yeah,
usually,
sure.
like this ADS CFT correspondence, they always see people take this large n limit, like the degrees
Yeah,
of
yeah,
freedom.
yeah.
So where exactly have you used that in the previous
I have
analysis?
not
Like,
actually.
you
So uh, so you know, I have not exactly used anything basically, except for the fact that the symmetries on both sides would be equal. So I mean, the idea essentially is that when you're looking at when you're looking at something like super Yang Mills and so on, and so there, I mean, so large n, as you know, simplifies life, right? So you can sort of focus on some particular sets of diagrams. Since we didn't do large n, I'm a little sort of hesitant to try and start a discussion here about that. But the idea, in a sense, so at least the idea from my perspective, is that if you're given the sort of, I mean, bare bones of, I mean, holography, how are you going to build it up? Okay, so in the sense that, suppose Malda Sena is obviously a tremendously smart guy, and there were all those people before him and after him as well, and they have figured out a particular thing that works, right? In the sense that, I mean, ADS5 cross S5, string theory on ADS5 cross S5 is dual to supersymmetric Yang Mills, but that's one of them. So so the large n is going to be related to a supergravity approximation on the bulk side as well. But the idea is that, can you do something with just symmetries, and can you push what is sort of like the, I mean, bare bone structures from which you can build something up? For that, what I try to stress is that you need to match symmetries on both sides, and if you can do that, then perhaps you can also try to. So for our case, all we needed to do was needed to see that the partition functions actually match, right? So in a sense, so we just by doing this, we can actually push a lot of the things through for the three-dimensional ADS and two-dimensional CFT, because you have this power of infinite dimensional symmetries out here. Things become simple. And for example, the example that I showed you, you can reproduce what is going to happen for for these what the say the Cardi formula reproduces what the Bekenstein-Hagen entropy is. Of
Right.
course, when you're looking at particular things and you're looking to try and understand more clearly, it of course helps if you have a particular example. And there, the rest of the things that you're saying, some of that would be useful there. But the idea, at least again from my side, I would perhaps like to think of this as something which is beyond string theory as well. You don't. It would be good if you did not need to assume string theory to get this. So that was the idea of trying to give this in this way, because you could do the same thing. For example, if you're looking at de Sitter, you could think of similar things when you are looking at flat space. You could so you could actually look at more things like this, as you had asked earlier. What is if there are sort of different boundary conditions, you might not get the same same sort of symmetry algebra. So there are these alternative boundary conditions which you can put on ADS3, which are not Brown-Hanot boundary conditions. Then that leads to an asymptotic symmetry algebra, which is not the same. But you can again play the same game with symmetries, and you can try and see if things like counting like arguments in those particular field theories also work out. So we have been trying to do things like this, and some of it has worked out. So that's a line of thought that you can actually pursue and see how far you can go without trying to so in a sense, the prescription of holography in my mind is that you look at what the asymptotic symmetries of gravity in certain dimensions with certain boundary conditions would be. So that defines for you some sort of quantum theory of gravity in a certain space-time. And the dual theory is going to have these symmetries, these asymptotic symmetries will be the ones that are the the global symmetries of a dual field theory. You can start off with that and see how far you can go. So that's sort of like the idea that I take when you're trying to move beyond ADS to other things. So yeah.
Okay. Yeah.
So any more questions?
So this hello.
Yeah. Please.
So this infinite dimensional algebra is very specific to D equal to 2 CFTs, right?
That's right.
For
That's
for
right.
higher D CFTs, it is only the global parts. But from the bulk side, if we fix this type of boundary conditions, then what would be the asymptotic symmetry algebras? Would it be infinite dimensional again?
No, if you're looking at ADS, for example, if you're looking at ADS 4, ADS 5 and higher, the ASG always just is going to reduce to just SOD2 basically. So that is something that always would go through.
But for the flat space times, the BMS4 is infinite dimensional,
True,
right?
true. That's why you would also think that the dual field theory also, I mean, inherits this infinite dimensional symmetry.
I see.
So yeah, that's why, you know, in a sense that what we want to do is that we want to say that the symmetries of the field theory are also infinite dimensional, and there is
Even in
even in high
even in
dimensions.
higher
Yes,
dimensions,
yes,
right?
yes. That's well. Again, this is going to take us too far astray, but that's what I mean. You know, some part of my work has been trying to address. That, you know, if you have these field theories also in higher dimensions with infinite dimensional symmetries, could you have some fun with them?
Okay, thanks.
Yeah, sure. Any more questions? All right. So lastly, we have our you know, well, you have your talks starting on December 1st. So December 1st and 2nd, I have not sent out the email yet. I've been a little lazy with that. I'm sorry. But does 11 o'clock sound okay to everybody? We could have 11 to 1 o'clock for 4 talks the first day, and 11 to 1 o'clock for 4 talks the next day as well. Does that sound all right?
Yes.
Very good. So you guys have half an hour each, okay? So it's not going to, you know, stay 1 o'clock. I mean, I would presume that we will go until 1:30, I guess. But remember to structure your talk such that you finish in half an hour. Maybe 25 minutes plus 5 for questioning, but there will also be interruptions in between. So yeah, so approximately that, okay? And I will also send out an email which says when you need to submit your reports, as a few of you were saying you wanted a few more days, so that will be that. But I also wanted to say that there are going to be there's going to be either one long or two short. I mean, not short, but you know, I will give you assignments for the you know, half of, I mean, for the part of the course that you have not got assignments on. So you are going to get you know, I'm not decided whether I'm going to stitch it all in one, but that's going to be something that's going to be due before the 8th, I think. So you guys will get a week, and you are going to get an assignment which is probably due on the 7th. Okay. I'll send out the assignment to you either on the 1st or on the 2nd, or maybe on the Monday, so that you have a clear week. So you need to send that back to me on next Monday, that's 7th, and your reports will also be due probably on the same date. So that's what we want to do. And if there are, you know, last minute questions regarding what your projects and so on, drop me a line, and I'll try and answer them. All right,
Sir,
guys. Yeah. So there was a question.
yeah.
Rishi,
Could you
yeah.
upload the videos of the lectures?
Yeah, that's quite a bit of work, because I have not been following up on that. So which ones do you need?
I just need the one last Monday, like this
Last
Monday.
Monday?
I
Okay,
want.
so I'll try and do that, but I mean, the point is I've not been very systematic in trying to do this. It might take me a little while to do this, and yeah, you guys have a talk. I mean, unfortunately, the next day I also have a talk, which I have not even started to write. So this weekend is a little bit of a problem. I'll try and see if I can do that, but no, you know, promises actually. Okay. So maybe I can send this particular file to you or something. Just drop me an email about which date, okay? And then maybe I can either share it with you or just put that thing on YouTube or something like that.
Yeah.
Right?
Okay.
Okay, good.
And we are not having a lecture on Monday, right?
You are not having a lecture on Monday. So this was the last lecture, and well, I hope you guys had fun. It would have been more interesting to teach face to face, but I'm glad this worked out reasonably well. And it's infinitely more more interesting to have you, at least some of you, ask a few questions rather than record these lectures on my own and just put them up on on the web, which I was doing for the last course, which is pathetic. But anyway. Okay, so I realize that I'm actually recording these things. I should stop recording. Just give me a second. Yeah.